Okay, hello and welcome to this symposium keynote lecture for session C 4.7 on the development status of the Synergetic Air-Breathing and Rocket Engine, or SABRE, under development by Reaction Engines. My name is Simon Feast and I am Future SABRE Studies Lead at Reaction Engines. My background on the SABRE program started out on the technical side, working on a number of programs, primarily including heat exchanger design and testing, but I'm also very fortunate to have been involved in quite a broad range of activities, and in more recent years my role has been focused on technology strategy, as well as our advanced studies on future launch vehicle applications. So it gives me great pleasure to present to you today on this exciting project, about our current progress including some of our recent successes, as well as our future plans. I'm going to start by introducing the SABRE engine and its perceived benefits, and then take you through a high-level description of the development program, followed by some of our anticipated next steps. Before we jump in, I'd like to tell you a little bit about the business. Reaction Engines was first formed in 1989 in the UK with a pure focus on SABRE and aiming solely on the development of low-cost access to space. Since then, we have grown to around 200 people and have offices in both the UK and the US, and we have now a much broader strategic portfolio which, aside from space access, includes high-speed flight and additionally pursuing a number of other adjacent markets through a dedicated part of the business known as Applied Technologies. Our headquarters are based in the UK at the Culham Science Centre in Oxfordshire, and nearby we have a test facility at the Westcott Venture Park in Buckinghamshire. Our US office is based in Colorado, in addition to another testing facility. We also have a good working relationship with both the UK Space Agency and ESA, who have both been incredibly supportive to the program to date and continue to give us a really great level of support in both technical review of the SABRE program, as well as positive guidance around our forward plans. Additionally, I should mention some of our key partners, including BAE Systems, Rolls-Royce and Boeing, who we are very proud to be working with and very excited to see some of the great ideas starting to emerge from these relationships. So, to introduce SABRE, let's take a look inside and familiarise ourselves with what it is, the different systems involved, and how it operates. The SABRE is a single propulsion system design which combines jet engine and rocket engine technologies. You will see some of these technologies that are common to gas turbines at the front, but also technologies more associated with rockets at the back of the engine. Both of these systems work together to create an air-breathing rocket engine. Unlike a pure liquid rocket engine, which carries both its fuel and oxidizer on board the launcher, SABRE allows us to burn its fuel using atmospheric air during the first part of the ascent trajectory. As such, SABRE is intended for winged launch vehicles with horizontal takeoff and landing. In this air-breathing mode, air is captured at the air intake, which during supersonic flight speeds decelerates the air back to subsonic inside the nacelle. The airstream is then split into two, with some of the air supplied to the core air-breathing engine in the centre, and the remainder through a bypass duct and burner system around the outer perimeter at the base of the engine. The air-breathing core is very much like a gas turbine, and uses a turbo compressor to supply high-pressure air to the main combustion chamber. The engine operates in air-breathing mode during the initial part of the ascent trajectory, up to an altitude of around 26 kilometers and a flight speed of Mach 5. During this time, the air temperature increases due to the substantial kinetic heating involved in decelerating the air back down to subsonic speeds within the nacelle. And at Mach 5, as a result of this, the air gets up to around 1000 degrees C, well beyond the performance and materials limits of conventional gas turbines. To manage this issue, a high-performance heat exchanger known as the air pre-cooler is inserted upstream of the core engine, which cools the airflow back down to near ambient conditions. This provides the air-breathing core engine with a single, stable design point, whilst enabling it to operate up to flight speeds around double that of current air-breathing engine capabilities. However, still using relatively conventional and well-proven jet engine technologies. Beyond Mach 5 and at higher altitudes, SABRE transitions over to rocket mode, reverting to a pure liquid rocket engine, drawing upon a separate but now reduced demand of liquid oxygen stored on board the vehicle. However, both engines use the same integrated air-breathing and rocket nozzle. If we look at the cooling cycle used to achieve this, we can see how the engine works thermodynamically. The engine's fuel is cryogenic liquid hydrogen, here shown in purple, which is stored at very low temperature and is used as the overall heat sink for the cooling cycle. The pre-cooler is able to continuously remove heat from the air through the use of a closed circulating loop of high-pressure helium, shown here in green. The helium transfers heat indirectly from the high-temperature airstream at the pre-cooler to the low-temperature hydrogen. The SABRE cycle is actually able to usefully exploit this large temperature difference by imposing an internal heat engine cycle between the high-temperature heat source and low-temperature heat sink, using the helium as a working fluid to drive the air-breathing engine's main turbocompressor and helium circulator turbines. At lower flight speeds, and for example from takeoff, when the intake air temperature is much lower, the heat input by the pre-cooler is substituted by a separate heat exchanger and pre-burner to top up the temperature of the helium circuit. This provides a near constant turbine operating point and simplifies the overall design and performance modelling of the engine and turns the problem of the hot air into a solution to benefit the overall system design. So summarising the engine's operation, at point 1, high-speed air entering the engine heats up as it decelerates to subsonic speeds. At point 2, the air pre-cooler cools the high-temperature intake air to near-constant compressor inlet conditions. At point 3, the core engine compresses the airflow and rejects heat to the liquid hydrogen fuel via a closed helium loop. As the cooling cycle ultimately rejects its heat to the hydrogen fuel, for SABRE, the demand for fuel flow as a coolant exceeds the fuel flow that is required for stoichiometric combustion. So at point 4, a bypass burner system is used to burn the excess hydrogen with additional air captured by the intake. At point number 5, a separate rocket engine is used for flight speeds beyond Mach 5, which allows the vehicle to operate up to orbital velocities. And at point 6, the air-breathing and rocket engines are integrated together using a common nozzle. So what SABRE gives us is the efficiency of a jet engine where we need it, but then also the performance of a rocket with vastly improved characteristics over a wide speed range. When you compare SABRE against other engine classes, you can see that it has a very good air-breathing specific impulse across a large Mach range, but also an extremely competitive thrust-to-weight ratio across all operating modes in a single integrated design, making SABRE a perfect solution for accelerating a winged vehicle from zero forward speed on the runway up to the high altitude and velocities required for space launch. So how do these benefits translate into space launch vehicles? Well, the weight saving achieved by introducing an air-breathing capability has a significant impact on the overall launch vehicle design by improving the overall mass fraction of the system, which can now be used to introduce systems such as wings and undercarriage to allow full vehicle recovery. This leads to reduced operating costs and complexity, and an increase in launch cadence between missions, as well as an increased reliability by allowing for a robust and incremental vehicle development program. Winged vehicles also have a wide mission abort envelope, offering the ability to recover payloads and upper stages in the event of an abort. What's really interesting is that SABRE has the true potential to enable single stage to orbit launches. However, the concept is scalable and can be operated purely as the first stage of a multi-stage system design. As such, SABRE provides a step change in technology for space access, improving on and enabling many disruptive features that are considered highly beneficial to the next generation of launchers, including system reusability, improved mission operations, increased reliability, and the capability to abort the mission and safely recover the vehicle, including its payload. So, turning now to the program, SABRE offers a practical development approach drawing upon near-term technologies. Its modular and scalable architecture allows for parallel systems development with an extensive ground test program. This allows us to structure a development program with a sensible approach to risk by working on critical subsystems and technologies to improve their readiness levels whilst simultaneously maturing the overall integration design. As you can see, the SABRE engine is broken out into three major subsystem groups, including the nacelle systems group, the air-breathing core engine, and the rocket engine systems, which can all be extensively and independently developed ahead of integrated testing. The SABRE program can also draw upon the well-established expertise and facilities available across government agencies, industry, and academia. Focusing now on the air-breathing core, we are continuously optimizing the flight engine design and have a well-structured subcomponent technology program, leading to an integrated test of several of the critical core subsystems on the ground. This program is referred to as Demo A. I'm pleased to say that we have recently passed a preliminary design review with ESA for this project, and also developed the test facility requirements. There are also a number of technology challenges which we are working on, along with the support of suppliers and partners to ensure we have a successful test program and ensure the performance and operability of the flight design. However, we would positively welcome you to get in touch if you have any experience in the areas listed. So here's an overview of the Demo A program. As you can see, the experimental core engine here is not tightly packaged like a flight engine would be, and this is intended to provide easy access to all the subsystems, allowing us to incrementally test and replace the hardware over a number of builds. What we aim to get out of this program is to develop the core engine technologies and also verify the various performance models and control logic. It is also important for us to demonstrate a controlled startup and shutdown, as well as stable operation over a wide range of throttle conditions. We also hope to measure the cycle's tolerance to component inefficiencies, but overall just to demonstrate a SABRE cycle in a scaled ground-based configuration. And an additional outcome will be to achieve component technology readiness levels of 4 to 5 at a relevant scale. Moving on to the rocket engine, Reaction Engines has carried out initial concept design work to understand the design to a level where we can specify the requirements and development needs. However, the rocket systems will ultimately be subcontracted to an experienced rocket engine manufacturer and can be developed in parallel to the nacelle and air-breathing core systems. The main technical challenges for the rocket is that we are looking for a staged combustion, high-pressure, closed-cycle design with liquid hydrogen. The SABRE rocket also needs to introduce a level of reusability, which is predominantly a challenge for combustion chambers, as well as, for example, turbopump seals and bearings. The SABRE rocket also shares an integrated nozzle design with the air-breathing engine, which is something we've been working on to de-risk for a series of nozzle design and experimental programs to more clearly understand the performance and critical issues. The rocket engine will be capable of being ground tested to a technology readiness level of around 6 or 7, making use of existing rocket testing facilities. The nacelle comprises of the overall containment aeroshell, which creates the boundary between the external and internal airflow. The nacelle has the task of capturing and conditioning the airflow into the core engine and bypass system. Several of the nacelle technologies are already being developed on the ground. This work is primarily focused around materials and structures development. However, the air intake and bypass burner aerothermal design is also being progressed through a combination of CFD and wind tunnel testing. Our most recent development on the pre-cooler has been its high-temperature test program, referred to as HTX. The objective of this experiment was to demonstrate the pre-cooler's functional operation at elevated air inlet temperatures and at representative heatant and coolant fluid flow conditions. The objectives of this program were to measure the pre-cooler's performance, get some verification on the mechanical design, and attain further validation of our aerodynamic and performance models. The target was to achieve the full Mach 5 equivalent conditions on the ground by designing a test rig capable of supplying very high temperature airflow across a physically scaled heat exchanger test article, however maintaining full aerothermodynamic flow conditions representative of its real operating environment. The illustrations here show the heat exchanger test article core and the containment structure used to direct the high temperature airflow through the core. The test site used a repurposed J79 jet engine to provide hot exhaust gas to around 1000 degrees C, with a mass flow between around 4 to 11.5 kilograms per second. To achieve the range of air inlet flows and temperatures, The J79 was run at a range of different conditions, with and without afterburner running, and compressor bleed mixing with the downstream flow. Another significant undertaking for this test rig was the requirement for a helium circulator operating at 200 bar and a flow rate of between 1 to 1.5 kilograms per second. The program was one of our most challenging endeavours yet, with the full design and fabrication of the test article hardware being performed in the UK, whilst a dedicated test facility was being prepared by our US team over in Colorado. The teams worked incredibly hard throughout all phases, constantly needing to innovate across all areas of the program to meet their challenging timescales and objectives. However, I am incredibly pleased to report that the overall program was a real success, achieving all objectives it set out to, and in October 2019 the test team achieved the full Mach 5 equivalent conditions, which represents a critical milestone in demonstrating this technology. The overall SABRE development program is a complex undertaking. However, we are working hard to ensure that it delivers maximum value throughout, addressing the critical technology risks early on, whilst incrementally bringing each of the SABRE subsystems together towards an integrated prototype engine. The program logic has been updated and continues to evolve as we work together, involving our numerous stakeholders and developing the future supply chain. We're committed to maintaining a pace that targets the overall delivery of a product engine to meet the launch market needs of next-generation launch vehicles. One of the next crucial steps for SABRE will be an extension to the current Demo A program to incrementally develop and de-risk the air-breathing technologies towards a flight engine specification. The Demo A Plus program will target a flight-integrated SABRE core demonstrator with subsystems designed close to final SABRE performance specification, aiming to bring all of the core engine systems to a technology readiness level of 5. This program will start with individual subsystem tests before moving to full integrated system testing, initially at part load and then expanding the test envelope to full operating conditions. The endpoint of this program will result in a core engine that is integrated together in a flight system configuration, with a compact layout using flight engine structures and ducting designs. Following this program, the Demo A Plus core demonstrator can be used as a basis for potential flight testing on an appropriate flight test vehicle, and will also pass on a significant amount of learning and design know-how into the full SABRE prototype core design. We're currently in the process of planning this work and hope to keep you updated as we make progress. One of the key benefits of SABRE is that most of the hardware can predominantly be tested on the ground. However, several aspects of the nacelle design will benefit development in a true representative flight environment. To achieve this, reaction engines are undertaking studies to examine the potential benefits of a dedicated flight test vehicle, known as the Hypersonic Testbed, or HTB. The HTB has the objective of de-risking the nacelle systems in flight, namely the coupled performance and operation of the air intake and bypass system. This would be a small and unpiloted experimental flight vehicle which has the capability of being powered by or carrying a small experimental nacelle to the appropriate altitude and Mach numbers for a representative SABRE air-breathing trajectory. The HTB would follow an incremental development and flight test program, and where possible utilize existing commercial and off-the-shelf hardware. The early part of the program would use a donor gas turbine in place of the SABRE core, and at a later stage may have the potential capability to test a small SABRE core such as the Demo A Plus system as part of a fully integrated small SABRE flight demonstration. Reaction engines are currently working across numerous studies to explore a number of concepts, looking at both single and twin nacelle configurations with the aim of identifying the overall feasibility and preferred system architectures whilst developing the preliminary requirements. Another attractive feature of the HTB program is that it would provide significant opportunities for the launch vehicle airframe technologies development, as well as offering a unique platform for testing other future hypersonic or reusable technologies. And finally, in terms of launch vehicle applications, we are actively engaged in external studies to examine and develop future SABRE launch vehicle concepts and define the final product SABRE engine requirements. These studies are aiming to optimize the scale and performance for both initial entry into service, as well as ensuring the SABRE design is scalable to meet the needs of both the future commercial and institutional launch markets, and are undertaking detailed trades between launch service and operational concepts, as well as the predicted system costs. These studies are also bringing a positive focus on identifying our future partners and the supply chain for the development of the full product engine and vehicle systems. So we've now come to the end of this lecture, and I'd like to leave you with a few conclusions. We are rising to the challenge. By continuing to mature and de-risk the critical SABRE technologies, we have positive engagement with UKSA, ESA and other national agencies. We're committed to delivery, with all major milestones to date passed, and we're progressing well with the air-breathing core demonstrator and related technology programs. We're also establishing key industrial partnerships and suppliers for the full development. Finally, we are unlocking the future by optimizing SABRE for the next generation of reusable launchers and identifying wider SABRE technology opportunities. Well, I hope this has been an exciting and informative presentation. I'd like to thank the IAF and the Space Propulsion Technical Committee for the opportunity to deliver this keynote lecture. It's been a real pleasure to give you an update on the SABRE programme and our forward plans. I'd also like to acknowledge the efforts of everybody at Reaction Engines and our partners for their dedication and passion in striving for a new and exciting future for space. So all that's left for me to say is thank you for your attention. Please do check out the full paper, and I hope you enjoy the rest of this year's conference.